In this movie, I'll walk you through the major project outcomes of the Aspire project. First, we developed quite some state-of-the-art software protections. You might remember that the goal of our project was to develop protections on 5 lines of defense, and for many of them, I only listed some, we did push the state-of-the-art. Many of these results are published in peer-reviewed publications and in 10 public reports that provide over 400 pages of information. All of them are available on the Aspire website. Now, developing the techniques in isolation was not enough. We also combined them into the Aspire Compiler Toolchain, or ACTC. This is an overall picture of it. You might remember it. We start from annotated source code, we send it through source level protection toolchain, and out comes partially protected source code. We send that through standard compiler, and we get object code, and then this is sent through some binary level protection tools that eventually produce a client-side application that is protected and server-side logic that will help in protecting the client side by means of online protections. During the project, we actually realized this whole toolchain. If you look at the source code annotations that we developed, here you have an example. These are extremely easy to use. Furthermore, you can configure the toolchain via JSON files, which are easy to read and edit by humans. If you look at the source level toolchain here, we implemented this as a plugin architecture, and with this architecture we iteratively deploy source code rewriting tools. All of these plugins take in source code and produce source code, and hence it's very easy to extend this with new protections. In this architecture, we already implemented a whole bunch of protections and source code rewriting steps. You see an overview here. There are too many to discuss in this video. Going back to this picture, if we look at the standard compiler, in our project we use GCC and LLVM and binutils, which are available to everyone. In order to let them produce enough information for the binary level processing, we developed a bunch of patches. These are very simple patches that everyone can deploy. They don't change the code that is generated, they only make sure that enough information is produced by the compiler and the binutils. And then with that information, at the binary level, we can rewrite the application, and that is done mostly in the Diablo link-time rewriter developed by Ghent University. So you see that in this toolchain, we invoke many plugins and tools. And to control all of this, we implemented the toolchain in Python and on top of the Do-It automation tool. This way, it's very easy to extend our existing toolchain and to add new passes and processing steps. Moreover, to facilitate the take-up of this infrastructure, we developed a Docker container that makes it very easy for everyone to set up this whole toolchain and start using it. Most importantly, however, we open sourced almost all of our plugins and the basic tools. We made a GitHub repository where you can find all necessary tools, third-party tools, as well as our own tools to set up the container, the toolchain, and to run it on some demo software. In total, we open sourced more than 250,000 lines of code that were developed by the project partners. In addition, to facilitate the take-up, we have extensive public documentation in the form of a report on the whole toolchain, as well as an open source manual. So there is a public manual and documentation. In total, they provide more than 150 pages of information and specs, for example, of the annotations. All of this is available on the Aspire website. Of course, just providing these tools will not suffice to let someone use them adequately. In order to use the toolchain effectively, it's important to understand how all the protections that are deployed with the toolchain operate and how they can be composed. And to that extent, we developed the Aspire reference architecture. This is a public deliverable that we produced in the first year and updated afterwards that presents a lot of knowledge. For example, it describes how multiple clients can be served from our secure servers for online protections. Within an application, it discusses how different protection techniques can be combined and how they can use the common communication logic to connect to the Aspire portal where the protection services are running. In detail, it discusses a simple request protocol that we implemented to communicate with a server, and also a WebSocket protocol that some protections need. Also in this document, we describe all the individual protections and how they operate. For example, for client-side code splitting, which is also known as instruction set virtualization, we describe what the protected application looks like, and we also discuss in detail all the individual execution steps when this protection code is invoked. For other protections, like client-server code splitting, we provide more details. For example, we document the whole API, we document what the packets look like, and we document the whole sequence of communication by means of a sequence diagram. Furthermore, we discuss how we can compose protections. For example, for anti-tampering protections, we discuss how attestators and verifiers, either offline or online, can be combined, how they can be combined with reaction mechanisms, and so on. This is all discussed in our reference architecture. In total, this document provides 99 pages of manuals to the Aspire protections. It documents the communication logic, all the anti-reverse engineering techniques that we can embed in applications, all the anti-tampering techniques, and then it also discusses the composability of the protections and the renewable forms that we have developed in the project. So with our open source tools and all this documentation, we think people can deploy our results to protect applications and to do further research into the protection of mobile applications. But that does not suffice. How does one know if the protections that are deployed are actually effective? For that, we developed the Aspire software protection evaluation methodology. First, we developed the Aspire security model. In this model, we formalize all relevant aspects for reasoning about the strength of protections, given some assets and security requirements and possible attacks on those assets. We have numerous models, for example, to model all relevant parts of applications, to model the properties of assets, to model the impact that protections have on the application and on metrics related to software protection. We also have models for all attack steps and models that formalize how different attack steps can be combined into attack paths. With these models, we can start to reason about attacks. Now, to model all possible attacks on certain assets, we decided to build on the existing approach of Petri nets. In such a net, you model the final goal of an attacker, and you model the initial state in which an attacker has not accomplished anything. And in order to reach his final goal, he has to reach some sub-goals, and he can do so by executing attack steps. Those steps are marked in black here. Those are the transitions of the Petri net. Now, the goal of these Petri nets is to reason about protections and attacks, and more precisely about the impact that protections might have on attackers. And to do that, we will adapt the Petri net if certain protections are applied, and we will estimate for each of the attack steps how much delay a certain protection might cause. And to do that, we did a lot of thinking about the complexity of individual attack steps. And we reasoned about the actions that are needed, the sub-goals that attackers want to reach, the experience and capabilities of attackers, all the tools and techniques they have available, and all the forms and representations of objects they're gonna attack and knowledge they're gonna use. And while we thought about this, we tried to link them to the potency of protections, to the stealth of protections, and to the resilience of protections. The end result was that for a set of concrete attacks, and here you see some attack tools based on graphs and traces, we were able to present more than 40 complexity metrics that we think measure aspects of programs that have an impact on the effort and the time attackers have to invest. These are complexity metrics because if certain forms of complexity increase, then attackers have to invest more time. Now, just having these complexity metrics obviously was not enough. And the reason is as follows. It might be that an original program is very simple, but then when you obfuscate it, it's very complex. But maybe the attacker in some attack step does not need to attack this form, but he might already have simplified the code to this form. Somehow we need to take this into account, and formally, if we have a Petri net with two transitions, to compute the complexity and the effort and time needed for this step, we need to use this representation. To compute the delay of the attack in this step, we need to use this form. To include this knowledge in our framework for metrics, we built on the work by Yadigari and al. From 2015, and we proposed a framework for resilience metrics. So in the end, we proposed a set of metrics which we think allow us to estimate the effort that attackers have to invest in specific attack steps. Of course, to be practical, we need to be able to compute those metrics. So if we look back at our toolchain, in this toolchain, we implemented support for computing the metrics. Our toolchain cannot just produce the protected client-side application, but it can also produce a self-profiling version of that application that collects information that's needed to compute the metrics. And the toolchain outputs metrics. In the near future, it will also be possible to feed traces to the tool to produce even more metrics the more complex forms in particular. So we have full tool support to measure the metrics and to generate the numbers on protected applications. And those metrics can be used when you're going to compute the overall effort on such Petri nets. Now we have to do so for multiple Petri nets for the different protected applications and compute different sets of metrics on them. And then of course we have to aggregate all the data and compare different sets of protections. To do that, we developed the necessary mathematical models. These are some formulas taken from a deliverable to aggregate all the data, that is all the metrics, and hence by comparing those numbers for different Petri nets, for different protected versions, compute which protections are better than others. Now, we did not only develop the formal methods and models, we also designed full tool support for this. Even more, we implemented all the tools. And so here you see a screenshot of what we call the Aspire Decision Support System Lite. With this system, experts can feed information into the Aspire knowledge base and compare different forms of protections. So with this system and all the metric support and the models and so on, we have sufficient tools to compare different sets of protections. In the project we went further, however, and we also developed a full decision support system that can automatically select the best protections given a set of assets in an application. For that, we developed a whole decision support approach. We developed optimization strategies, and those are based on game theory. Again, we did not only develop all the models and the optimization approaches, we developed a whole implementation, and this is called the Aspire Decision Support System Full. It centers around the Aspire knowledge base that stores all the relevant expert information. It connects to the ACTC to collect all the metrics, and it has various enrichment modules to compute the best combinations of protections. Now, we not only designed this, we also implemented this, and here you see some screenshots of the decision support system. It's basically an Eclipse plugin. Here as well, all tools are open sourced, there are public manuals and documentation, and the whole evaluation methodology is documented in over 400 pages of public Work Package 4 reports. That wraps up the technology we developed, but of course we not just developed it, we also validated it. You might remember that the goal was to take use cases from 3 companies, the 3 industrial partners of the project, and to send those use cases through the Aspire framework, which consists of the toolchain and the decision support system, to obtain protected use cases. In the project, we designed the use cases and we developed them, and we made the choice to go for realistic applications that are representative for real-world software that needs to be protected. So for our target platform and the use cases, we chose Android. We went for GUI applications, where the security-sensitive code is implemented in dynamically loaded libraries. This made our life much harder, but at least all the results, we know that they are valid for real-world complex software systems. Then how did we do the validation? Well, we started with identifying all the assets that need to be protected in the use cases, and we derived security requirements from those assets. And then based on the project plans, we decided what the best Aspire protections would be to safeguard those assets. The next thing we checked was whether or not our protection toolchain can actually deploy these protections on the use cases and on the assets, on the code fragments that implement the assets. The result of this validation was positive. With very few exceptions, all the envisioned protections could be deployed on the assets in the use cases. Next, we checked whether or not the deployed protections actually let us meet the security requirements. We basically cross-checked the deployed protections with the requirements, and the answer again was positive. Yes, at least in principle, these protections let us meet the security requirements, at least the most important requirements. Of course, this is only a theoretical assessment. The practical assessment still had to follow. Part of the practical assessment was that we measured the overhead introduced by the protections. And in all cases, this overhead was deemed controllable and acceptable for the use cases. The second practical part of the validation was to involve penetration testers. For all the 3 use cases, we hired professional penetration testers that targeted the assets in the use cases. But those were not the only experiments. We also conducted experiments with academic students, and we let them attack small toy examples, and we even involved the public in the project. To that extent, we developed and launched a public challenge where everyone could download challenges and provide and check their answers. I cannot go into the detailed results of all these experiments, but overall the result was that we met our initial project goal. Going back to our original economic model, these experiments confirmed that attackers are in fact delayed as envisioned by our protections. So here as well, the result was positive. Now, if I go back to the original picture, there was one more aspect to validate, namely the decision support system. And to validate that, we let it produce reports, and we handed those reports to professional security experts. Those experts confirmed that the information coming out of the decision support system and the selection it made for protections were actually good and useful. So here as well, the validation was successful. All of the penetration tests are extensively documented in the Work Package 4 reports and in a couple of peer-reviewed papers. Furthermore, the full validation report is public and it's available on the Aspire website. So let me summarize the major outcomes, and to do that, I'll go back to the original description of work. I have two fragments here from the description of work. We wanted to make software protection more trustworthy, more measurable, cheaper and more valuable. Concretely, we wanted to advance the state-of-the-art in software protection techniques. We wanted to build a software protection toolchain, develop metrics to measure the strength of protection techniques, develop a decision support system, and then use and validate all of that on 3 use cases. And that's exactly what we've done and what I've shown you in the previous slides. So overall, I think it is safe to state that overall the mission of the Aspire project was accomplished. Now these were just the technical outcomes. If I go a bit further and I look at exploitation and dissemination, one of our activities was an extensive SWOT analysis of all the technologies used and developed in the project. We also analyzed the technology readiness levels of all technologies, and this was done of course in preparation of the take-up of this technology in the participating companies. We also involved external experts within and outside the partnering companies, and this is of course to warm them up for our results, but also to make sure that our results were actually useful for their settings and requirements. Very importantly, we open sourced most technology. We provided extensive public documentation and deliverables, so that's reports. To further ease the take-up and disseminate the results, we released 29 demonstration videos on the YouTube demonstration channel. In total, these videos provide more than 3 hours of documentation and demonstration of Aspire results. We already finalized one successful transfer of IP from an academic partner to industry, and we are working on more. One academic partner is working on a spin-off. We know that the industrial partners are taking up results in their products and in their business units. And during the project, we organized 2 software protection workshops with over 90 participants in total. With those, we strengthened the European research community in software protection. Finally, we published 17 peer-reviewed publications, and we are planning to write many more. This joint effort has already started. So if we combine these results and activities with the technical results, I think we can actually state that we went beyond expectations and we achieved more at the end of the project than we could ever imagine at its beginning.